Okay, so for the second practical for today, we're going to learn how to count the cells using a hemocytometer, or in our CIE, sometimes we use the word counting grids. Same idea, counting grids or hemocytometer. So what we're going to use, this hemocytometer to estimate the number of cells or the cells organized in a whole slide or field of view using a sample or using a grid. Okay. So what's the hemocytometer? If you look at the structure of hemocytometer, it will be something like this. This is a picture of hemocytometer. So if you look at his hemocytometer, you will have the sample loading valve here, these two chamber. Can you see that? These two chamber, and they have a groove. Can you see the groove? Okay, so I will tell you guys more what is the function of the groove and what is the functions of this chamber. Okay, so the hemocytometer is a counting chamber device originally designed and usually used to count the blood cells. So that's why they call hemocytometer. Hemo means that's the blood, the blood cells, red blood cells. So this chamber, it consists of the thick glass microscope slides with rectangular indentions that create a precision volume chamber. So this chamber is engraved with a laser edge grids for a perpendicular lines. So this design is carefully crafted so that the area bounded by the line is known and the depth of the chamber is known as well. So by observing a defined area of the grid, it's therefore possible to count the number of cells or particles in a specific volume of fluids, and therefore calculates the concentration of the cells in the fluids overall. Okay. So let us look at this counting grid. Okay, so from the top view of this hemocytometer, top viewer, you can see that we have this structure. Okay, so this part is the groove. Okay, and then at these two platforms here, you will have the counting grid. You only will see under the light microscope or under the light, you may see the grids. Okay, so if you view it from the side, this side view, you will see something like this. Okay, if I cut it, a side view, so you will see the groove. And then you will see the sample loading well. And then the groove again. Side view. So this is the part where we're going to load in with our cell suspension. And then we're going to cover it with the cover slip. Okay. So this is a cover slip. Okay. So what is the functions here is, we do know what is the thickness of this well. Are you clear? The depth of this well. So the depth of this well generally is 0.1 mm. Okay, or equivalent to 1 × 10⁻⁻² cm. Okay, equivalent to 1 × 10⁻⁻² cm. Okay, I will tell you guys why I changed to cm. Okay, okay, so what is the function of the groove? Function of the groove here is for overflow. Are you clear? So let's say you put a sample too high. Then with the cover slip will press it. So when cover slip press it, so the remaining solutions now will flow into the groove so that we have the definite volume. And volume is very important later because we want to calculate the concentration of the cells. Okay, so now next thing what we're going to do here is we zoom it in here. Okay, what you can see here is you can see 9 grids. Okay, 9 grids. So generally, it depends on what kind of cells you want to study, but normally we're going to choose the top right and left, top right, bottom left and bottom right to study. Are you clear? So normally what we do here is we're going to choose top left, top right, bottom left, bottom right to study. Center, no. Are you clear? We won't study the center. Now, if you measure, okay, the most, our hemocytometer will tell you what is the dimension of this grid. Okay, so let's say, for example, normally is 1 millimeter by 1 millimeter. Again, one grid, look here. Are you clear? One grid is 1 millimeter by 1 millimeter, or equivalent to 1 times 10 to the power negative 1 centimeter, or equivalent to 1 times 10 to the power negative 1 centimeter. Okay, that is a dimension. Okay, so if you further to enlarge this chamber, then what you can see is this chamber is divided into 16 square. 1, 2, 3, 4, 5. 1, 2, 3, 5. Okay, at the side you have extra lines. Something like this. Okay, but we do know that, okay, the dimensions, okay, for one chamber grid like this is 1 mm. Chamber here is 1 mm. Okay, now what we're going to do here is we're going to calculate, okay, or count whatever cells that located inside the grid. Let's say cell number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, for example. Are you clear? So all inside we count. So this one we count. 1, 2, we count. Okay, we count the cells. Are you clear? Now, how about the cells that partially inside the grid, partially touch the outer line? Then we use the L rules. Now, what I mean L rules? L rules actually, before we view it, then we define which L rules we want to use. Okay, so we can use either top and left, or top and right, or bottom, bottom and left L, or bottom and right out. Now, if let's say I already define, I'm going to use a top left L shape. So means that I'm going to use follow, okay, I'm going to read these two. So only the cell that touches, okay, only the cell that touch these two lines, I will count it. Okay, so let's say, for example, I have a cell that touch. Okay. Okay, touch the middle lines like this. So those I will count. Yes. But some of the cells that touch, okay, not these two lines, then those cells I won't count it. So I only count the cells that touch, okay, the cells that touch that two line. But I have to define it. I cannot see it already. Oh, now I want to use a top and right. Oh, I want to use the bottom and left. Cannot. You have to define it. Then you use it. Okay. Then we use it for all chamber. So it means that I'm going to use it. Let's say, for example, I'm going to use a top and left, top and left, top and left, top and left. Are you clear? So what we can have here is we can get the first thing, how to do the calculations. So first step, we can count the total number of cells in 4 quadrants or 4 chamber. So equal to n. Okay, I put it equal to n. You need to know how to derive the formula, yeah, here. Okay, count the total number of cells in 4 chamber, which equal to n. And then second, we get the mean. number of cells in one chamber. So we're equal to n over 4. Okay, mean number of cells in one chamber were equal to one chamber equal to n over 4. Okay, second. Now look at this. This is one chamber. This is considered one chamber. Yeah, one chamber. So what is the volume in one chamber? Because this one is something like a well, right? It's something like a well. So you got the depth, then you get the length, and also the width. Clear not? So I can know the volume. So what is the volume of one chamber? So equal to the length multiplied with width multiplied with the depth. Correct or not? So what is the length? Length is 1 mm. The width also 1 mm. The depth is 0.1 mm. But because we want the concentration, because we want to know the concentration of cells in how many cells per ml. And we do know that 1 ml equivalent to 1 cm cube. Correct. So volume of one chamber now we have to calculate. So we convert this one is 1 times 10 to the power of -1. This one is 1 times 10 to the power of -1. This one is 1 times 10 to the power of -2 cm. So total will be 1 times 10 to the power of -4 cm cube, or simply is 10 to the power of -4 cm cube. Are you clear? So now the third step, we can calculate the concentrations. So concentrations of cells per cm cube will equal to the number of cells, or mean number of cells, divided by the volume. So mean number of cells is n over 4 divided by 10 to the power of -4. So 10 to the -4, you can bring it up. So it's n over 4 multiplied with 10 to the power of 4. So unit is cells per cm cubed. Okay, this is the formula. But it totally depends on how many times you count, how many chambers. Some in lazy, I count 2. I mean, let's say, for example, I'm hardworking, I count 8. So how we can get 8? How we can get 8? So we count from the bottom here and then top here. So total can count 8. So n over 8. So it depends on how many chamber you count. So it totally depends. So if here is 8, then we divided by 8. Are you clear? Okay, so then we can calculate the volume of one chamber, which is 10 to the power of -4. Again, this is just for today, okay? Because different hemocytometer, different area you view it, they have different units. So you need to actually follow the question. So sometimes questions tell you it's 0.2 mm. Then you use 0.2 mm multiplied with 0.2 mm, okay? So you have the mean number of cells per volume, then you can get how many cells per cm cube, okay? Any question, guys, so far for the calculations? Very simple. Now, let us go to our practical paper. Okay. So the gridded area of this hemocytometer, generally we have the lines, okay, 1 by 1 millimeter square. These are subdivided by 3 directions. So it may be 0.25 by 0.25 or 0.25 times 0.2. We have 0.2 times 0.2. So it depends on different area that we want to view. Okay. So then you can see that the raised edge of the hemocytometer hold the Coverslip of 0.1 mm of the marked grid, so giving each square a defined volume. Okay, so for us, we're going to follow, okay, can highlight. For us, we're going to follow, okay, we're going to use, guys, this area. Number 1, number 2, number 3, and number 4. And how we count? How we count? So we use L shape. So in this case, they use the top and left L shape. Okay, and the units here, can you see that is 1 mm by 1 mm with a thickness of 0.1 mm sample loading well. Okay, the thickness or the depth here. Okay, so we use this 4, so that's why n divided by 4. So the concentration of cells in the number or in the unit of number of cells per cm cube can be calculated by using the following formula. So total number, or we can see that the mean number of the counted cells divided by number of grids. Okay. Oh, sorry, wait, my mistake. Yeah, correct. Total number of counted cells divided number of grids multiplied 10 to the power of 4. Okay, so experiment 13.1, we can't do it, okay, now, okay, because we have to go back to the lab. What we're going to do here is you are required to estimate the total number of yeast cells in 10 ml, 0.5%. So what does mean 0.5%? 0.5% means that I get 5 grams and something like, suspend them in 100 ml of distilled water or buffer solution. Sorry. Okay, so I suspend. So it means that I measure 5 grams already, then put them into this 100 ml of distilled water. Okay, so make 0.5 gram. Okay, sorry, not 5 grams, 0.5%, not 5%. Sorry, my mistake. So it's 0.5% yeast suspensions by using a counting grades. Okay, so again, first we clean the hemocytometer and cover slip by using ethanol. Then you place a glass cover slip over the counting chamber. Then you can pipette the yeast suspension into the hemocytometer. Then place the hemocytometer under the microscope. Focus both, okay, onto the grid pattern and the yeast cells. But the issue here is when you observe the yeast cells by having 0.5 gram in 100 ml, what will happen here is the number of cells is too much for us to calculate. It may cover all the grid. You may not be able to see where is the grid at all. Are you clear? So we need to do the dilution. So first, I have 0.5%. So I can do the times 10-fold dilutions. Okay, when I dilute it, I get 0.05%. And then I load it and view. It's still a lot. Then I continue. It depends on how you look at it. So if still a lot, then I divide by 10 again. So I get the third one. Like for example, 0.005%. Oh yeah, then I load it in. I can count. Are you clear? Okay, I can do the counting. So, but always remember when you count by using this sample, this is called diluted sample. When you count a diluted sample, means that later, if I want to know the original sample, I have to calculate it back. Are you clear? I have to calculate it back. Okay, so suggest and describe modification to solve the problem. So first, what is the problem? So generally, it's overcrowded, too many cells to be counted. And also at the same time, you can see that you won't be able to see where is the grid because it's covered by all the grids are covered by the yeast cells. Okay, so suggestions here, you can do the 10-fold dilutions until you will be able to count the number of cells at that particular chamber. Okay, so after the modification, repeat step 1 and step 5 and count the total number of yeast cells found in 4 large corners of the square. So if cells are touching the 4 parameter sides of the corner square, only count the cell 2 sides, either 2 outer sides or 2 inner sides. Okay, so state the total number of the yeast cells found in 4 large corner square and calculate the concentration of yeast found in 4 large corner square. Okay, so let's say the total number. Okay, you do a simple calculations. Yeah. Okay. So the grids given here, we follow the grids. So this is the grid that we're going to use. So state the number of yeast cells found in 4. Let's say the total number of yeast cells equal to n. So calculate the concentration of yeast cells found in 4 large corner square. So means that we get the mean number. Okay, mean number of cells per chamber or per square. Since the question used the word square, so equal to n divided by 4. So what is the concentration? So concentrations, again, will equal to n over 4 multiplied with 10 to the power of 4, okay? Because we have done the, okay, you get the idea? So you can copy down. So mean number of the cells per square now is n over 4. Therefore, the concentration will equal to n over 4 times 10 to the power of 4. The units will be cells per cm cube. Just now I already derived why we multiply 10 to the power of 4. Okay. Okay, so next. So we want to estimate the total number of cells in 10 ml. So it means that 10 cm cube. So it means that whatever I calculate here, the concentration actually refer to. If I calculate the concentration here refer to, because I have done the dilutions, right? I've done the dilutions. So it's 0.005. Okay, so it's 0.005%. So if I want to make it into 0.5%, I have to multiply with 100, correct or not? So in this case, what is the concentration of cells in 0.5% yeast suspension? This will be equal to n over 4 multiplied with 10 to the power of 4 multiplied with 100, okay? Why multiply 100 or 10 squared? Because when you go back here, you multiply with 10. You go back here, you multiply with 10. So total, you multiply with 100, okay? So equal to n over 4 times 10 to the power of 6. Okay, cells per cm cube, per cm cube. So what's the total number of cells now in 10 ml? So total number of cells will equal to n over 4 multiplied with 10 to the power of 6. Okay, because per cm cube. So now we have 10 ml, right? So multiply with 10 ml. So then you get n over 4 multiplied 10 to the power of 6. Total number of cells, okay, in 10 ml. So n over 4 multiplied with 10 to the power of 7. Okay, I don't have the data. We don't have the data, so therefore I use the n to represent the total number. Okay. Copy down. Okay, get the idea how to do the calculations now. Okay, so now we continue with experiment 13.2. This is a past year paper. Okay, you can try the questions. So it suggests how you can use this apparatus. Okay, could be used to estimate the number of cells per cm cube of the culture. Okay, but now can you see that we use a different one already? It's not 1 mm, it's 0.2 mm, 0.2 mm. The depth is 0.1. So you need to recalculate the volume. So it's no longer times 10 to the power of 4 already. This one no longer already. Okay, times 10 to the power of 4 because it's 1 mm by 1 mm by 0.1 mm. Okay, the length, the width, and the depth. Okay, but now it's no longer, depth is still remain the same, but the width and also the length already changed. Okay, it's no longer no longer 1 mm already, it's 0.2 mm. So it means that when you calculate it, you make a calculations, make sure that you readjust or recalculate. Okay. So suggest why the result in table 13.3.1 may not be reliable. So find out why it's not reliable. Okay, and suggest explanations why the cells actually increase in the number. Okay, I'll show in table 13.2.1. Okay, so now we come to experiment 13.3. So artificial insemination is one of the methods used to assisted reproduction that we have done. Okay, for large mammal, we have done this before. So for many years, the horse breeder have collected semen, okay, sample from the male horses and used these to inseminate female horses. Success rate have been quite good. However, due to the sample contain the live sperm cells, the process needed to be carried out quickly. So new technology exists to allow horse semen to be frozen in a small plastic straw. So the semen sample can now be stored for many years and transport all over the world. Like for example, we don't use for the horse only, for the tiger, for endangered species, we can actually transport or send it to other, regions or other zoo. So each 0.5 cm of straw can hold 7.5 times 10 to the power 7 sperm cells. So a typical sample, horse sample, contains 7.5 times 10 to the power of 9 sperm cells. Okay, so calculate the volume of the typical horse semen sample. And to inseminate one female horse, we need so much of the sperm. So calculate the minimum number of straw needed to carry out this process. So later, please register your attendance. Okay, for question A1 and A2, okay, do the calculations. And then this one, you can do it later. How you can use this apparatus to estimate the number of sperm cells per cm cube of the semen and describe how the technicians decided which sperm cell to include in the count. So how we can, okay. So you can see that in this case, a different type of the hemocytometer. Can you see that? It's 0.25, 0.25, and 0.1 mm. Okay. So now, next one, just now I said that's to register attendance, calculate A1 and A2. And then next, C. We reference the figure 13.3.1, calculate the number of sperm cells per cm cube of the semen. Okay, based on this, I want the concentrations, right? Yeah, concentration, number of sperm cells per cm cube, okay, in this. So you can see that each number represents sperm cells which are counted in the sample. Each star represents a sperm cell not counted in the sample. So you can see that in this case, they have 3 lines, okay, 3 lines, the center line. So you can see that those already put in the number means that they're already counted. So you don't need to count how many cells already. In this case, you have the total number of cells of 20, not mistaken. Again, those touches the lines is not counted. Outer lines, can you see that outer line are not counted? Touches the outer line, not counted. So you can see that they use the top and the left. Okay, top and the left. So those the third line. Can you see that, guys? If you look at the outer line, if you took the outer lines belong to different quadrants already, different chamber. So therefore, we don't count it. Can you see that? This one that touch the outer lines, we don't count it, even though it's left and top. So the one I show you in the discussion just now is this middle line, these 2 lines. Are you clear? So touches these 2 lines, the cell we still count. So that's why number 6 counted. Okay. But you can see this cell is not counted because it belongs to the bottom and the right. Can you see that? The right bottom we don't use. We use these 2. So therefore, you can see cell number 1, yes, counted. Cell number 6 counted. Okay. Can you see that? Cell 21 also counted. So total we have 21 cells here. Okay. So please register your attendance. Okay, so you are given 10 minutes and then I will discuss the question with you guys. Okay, so please register your attendance for today. Let me check whether the form is open up. Don't start first. You can calculate, on a piece of paper and then register it later. Okay. Okay, it's on. Okay, you can register attendance. So 10 minutes. So come back at 1:40. Okay, 1:40. Then we do a simple calculations, and then the rest of question you can do it again after that. Okay, you're done. Nice. Not all. Okay, extend another 5 minutes. Okay, not all of you registered yet, the attendance.